Welcome back, class. Welcome to our third and final conic section. Today and the rest of this week, I want to talk about the hyperbolas. And just like we've done with parabolas and ellipses, we will start with talking about hyperbolas that are centered at the origin, and then later on in the week, we will start shifting these around a little bit. To give you a little definition of hyperbolas, it is the set of points, so any point that's on one of these, what we're going to call branches. It's the set of points where the difference of the distances from these focal points is a positive constant. Okay, again, the definition always sounds a little bit weird, but just to kind of give you an idea of what this definition means, it's telling us that if I plotted another point, and let's switch the colors here. If I plotted another point on the graph, this point here, x, y, the distance from this point to that first focal point, let's call that D1 again, and the distance from this point to that second focal point, we're going to call that D2. If I subtract those distances, D1 minus D2, and I take the absolute value, in other words, I'm only going to be focusing on a positive distance here, that distance will be the same as the subtraction of these two distances. So no matter where the point is plotted, that distance between them is going to end up being the same value again. Now, right away, you can start to see there's a few things that are going to be similar here. We are going to be talking about focal points when we're talking about these hyperbolas. We are going to be looking at some of these different distances. But to kind of give you an idea of some of the relationships, hyperbolas are actually very directly related to those ellipses that we saw last week, as well as circles that we saw before. So I wanted to give you a quick little demonstration of these hyperbolas and talk a little bit about some of the things you might notice. First of all, notice the equation that we have up here, okay? This looks very much like the equation of an ellipse. We can see that it says equals 1, just like an ellipse. We can see the fraction here, the x squared over something plus y squared over something, just like an ellipse. However, you notice that what's showing here in the graph is not an ellipse. This is what we call a hyperbola. And it has to do with this value down here, this a value. So we're going to start moving that a value around. Right now, I want you to notice that that a value is negative 10. And as I move it, you'll still see that that a value remains negative. And we can see that ellipse is almost getting a little bit more narrow as that a value approaches 1 or approaches 0. The key is, though, that the a value right now is negative. Now, if you think about the fraction up here, if that a value is negative, that's actually going to make that whole fraction a subtraction. Because if I do y squared and I divide by a negative number, it's going to be the same as subtracting that value. So what I want you to think about is the fact that this negative a value here that's causing this hyperbola actually equates to having a minus sign in the equation. Now, as that a value gets closer and closer to 0, we see those branches becoming more and more narrow. Once that a value actually becomes 0, the graph disappears, and that's because dividing by 0 is actually undefined. Once that a value becomes positive again, now we're back to what an ellipse would look like. Again, if the a value is positive, it would make this fraction here be a positive fraction, which would leave us with that plus sign that we're used to seeing in an ellipse. And right now you can see that we have an ellipse that is opening horizontally. So it's more of that horizontal ellipse. And that's because my a value right now is actually smaller than the 4. So remember that if the bigger number is under the x, then the graph kind of opens up horizontally like the x-axis. Once that a value gets larger, now watch what happens when the a value becomes 4 exactly. Oops. When the a value becomes 4, so in other words, when the two denominators are the same, we actually have a perfect circle. Now, once that a value becomes greater than 4, so if we start making that a value 6 and 7 and 8, now we see that this is an ellipse that is opening vertically because now the larger number is below the y. So again, just to kind of reiterate, the format of the equation is going to be the same for a hyperbola versus an ellipse. The big difference is going to be that in a hyperbola, you're going to have a negative because that a value is becoming negative, and again, that's going to really make this fraction here become negative. So these are the hyperbolas that we're looking at. Now, let's kind of summarize that and go back to a couple of things that then we can kind of conclude from this. We know that actually, let's start with an ellipse since we know those. We know that in an ellipse, the equation is x squared over something plus y squared over something equals 1. We just saw that a hyperbola equation is going to look very similar, except that we're going to have a minus in place of that plus. And again, that was just that a value being negative. But it's, whoops, I apologize. It's still going to say equals 1. So a lot of similarities in the two equations. They're going to look very similar to each other, so we are going to have to watch for that a little carefully. Now, a couple more things, though, that go along with these hyperbolas. So first of all, I want you to notice some of the key terms that we're going to be talking about. Hyperbolas are going to have two what we call branches. So our branches can either open up or down, like in this one, or they can open left or right. We'll see the difference momentarily. Hyperbolas, just like ellipses, are going to have a center point. That center is going to be directly between the vertices. The vertices are going to be on the actual branches themselves. There are going to be two focal points. Just like in the ellipse, the focal points are going to be inside the branches. Just like in the parabolas, the focal points are inside the branches as well. Then we can talk about the distances. The distance from the center point to the focus point is that C value. That is no different. I'm going to write it down here at the bottom. That's no different in the ellipse than in the ellipse. The C value is the distance from the center to the focus. Okay, the A value is the distance from the center to the vertex. And what we haven't shown on this picture here is the B value. Technically, in a hyperbola, the B value is used, and just like in ellipses, I'm going to say that the B value takes us from the center to the covertex. Although you'll notice that there's no covertex actually graphed on this picture. That's because the covertex, although we will talk about it, and it is part of the equation a little bit, the covertex is not actually part of the graph itself. And that's why you'll notice that there's no covertex marked on the graph. Okay? The last thing I want to point out is this transverse axis here. This transverse axis can be either vertical, like in this case, or it can be horizontal. The transverse axis goes the same direction as the branches. So if the branches open up and down, then the transverse axis will go up and down. The transverse axis will contain both focal points, both vertex points, and the center. So all those key points line up on that same transverse axis. Now, using some of this information, looking at a couple of the equations. So once again, some of the key things that I want you to notice in the equation. In an ellipse equation, we're going to see a subtraction, okay? Just like we saw in those earlier ones. It's still going to say equals 1. That's one key that we're not going to be forgetting. But I also want you to notice this change. Okay, just like with ellipses, there is a relationship between the A, B, and C values, but it's a little bit different here. Okay, in fact, if we go back up to what we were summarizing here, remember with an ellipse, we knew that A squared minus B squared was going to give us a C squared. In a hyperbola, it's A squared plus B squared equals C squared. I generally tell people to focus on the fact that the signs change. So if your equation has an addition sign, then you know that this relationship will be subtraction, and vice versa. So there is a relationship, but it is the opposite of what we saw the last time. Okay, if we start looking at the graph, I want you to notice a few of these points. So here's these vertex points, and here's these focal points, and here is my center point. Remember that the distance to my vertex point is A. The distance to my focal point is B. So then you might ask, well, where is this? Oh, I'm sorry, the distance to my focal point is C. So then you might be asking yourself, then where is this B value? Well, I mentioned that the B value takes you to the covertex, although I said it's not actually part of the graph. Here is what I would call the covertex points. And so the distance from the center to that point, that's my B value. Okay, now, even though that point is not anywhere on the actual branches itself. So, here's the actual graph, this branch and this branch. And you'll notice that the focal points are, the vertex is on the branches, the focal points are inside the branches, the center is right between the branches. The co-vertices are there, but they're not really part of the graph. However, I want you to notice this rectangle. There's this rectangle that we've drawn here that connects the co-vertices and the vertices. And then with this rectangle, notice that there are these diagonals. And these diagonals are acting as asymptotes. Now, what is an asymptote again? Remember that an asymptote is an imaginary line that the graph approaches. We can use these asymptotes to help us actually sketch the hyperbolas. Once we know where once we know which direction the hyperbolas go, we know where the vertices are. The next thing we would need to know is these asymptotes in order to help us graph how wide the hyperbolas actually are. So we are going to use the co-vertices that are going to help us draw in this rectangle. With this rectangle, we're going to draw in those diagonals, and then those diagonals are going to be these asymptotes that we use. Now, because these diagonals are linear, that means that we should be able to write an equation of these lines. It's actually really easy to write the equation. Remember that lines we can use the simple equation y equals mx plus b. Since our center is at 0 and these diagonals go through the center, I'm just going to add 0 here for my b value. What I really need to figure out here is what is the slope of this line. Well, if you think about slope, remember that slope is rise over run. So what did we actually do here? We actually, starting at the center, we went up b units and we went to the right a units. So my slope is actually b over a. And I can use that to write an equation of this line. So this asymptote would have the equation y equals b over ax. Now what about this second asymptote here? This is going to have the same value. So if you think again, now I'm going down b units. I'm still going right a units. This time my equation is negative b over ax. So when we write the equation of these asymptotes, they are in the form of y equals positive and negative b over ax. Now I will point out one thing. You do not need to memorize the equation of the asymptotes. If you have a graph and you know how to sketch the graphs, which we're going to be doing shortly, you can write the equation of the asymptotes just by looking at the graph and finding your slope. Okay? Okay, so now we have a hyperbola that is opening vertically. So it has a vertical transverse axis. This means it's opening either up or down. Okay, everything else remains the same in terms of, the distance from the center to the vertex is my A, the distance from the center to here, that's my B, the distance from the center to my focus, that's my C. All of these features remain the same. The big distinction is what the order that the variables are in. So when the hyperbola was opening left and right, like in this one, you'll notice that the x squared came first, and then we subtracted the y squared. So I always say, just as a quick reminder, if the x squared is first, then you know it's going to open left and right, just like the x-axis opens left and right. If, however, like in this example, the y squared comes first, when y squared comes first, then you know it's going to open up and down, just like the y-axis opens up and down. There's always going to be a subtraction. So it's going to have to be one variable minus the other one, but it matters which one comes first this time. Okay, when we think about the asymptotes this time, and here's why I always hesitate memorizing the equation for asymptotes, because you have to really pay attention to the direction that it's going. If you wanted to know the equation of the asymptotes this time, so if I wanted to know the equation of this line, once again, think about my slope. We know that it's going through the origin, so plus 0 is not going to change. But now think about how I actually would find the slope. This time I'm going up a units, and I'm going right b units. So my slope is actually a over b this time. And for the other equation, now my slope is negative a over b. So what we're seeing here is that in sometimes, right now my asymptote for this one is either positive a over bx or negative a over bx. Whereas with this one, it was b over a. Rather than trying to memorize which is which, again, use the graph to help you write your asymptotes by actually looking at your rise and your run, looking at your A and your B values. Now it's time to put all this together and look at a couple of quick examples. Since a lot of this we've done, this will go pretty quickly. You'll feel pretty comfortable with it. Just pay attention to some of the key features. For example, as soon as you see that we are subtracting one of these variables, this is how we know that we're going to be dealing with a hyperbola. And since we have the x squared coming first, we know that this hyperbola is going to open left and right, just like the x-axis opens left and right. Since we're not doing anything to the x or the y values, that tells us that the center point is actually going to stay at 0, 0 today. So I can plot that center right away if I want. Now, for actually plotting vertices and all the rest of this, we're going to do it the same way that we did with ellipses. This value represents a squared, which means my a value is 5. Since it's under the x-axis, I'm going to be going left and right 5 places, and that's going to tell me where my vertices go. So at this point, I know my vertices are at positive and negative 5, 0. Okay, just like with ellipses, if it's under the x-axis, you're going left and right. If it's under the y-axis, you're going up and down. So when I get to this part of the equation, this is my b squared, which means my b value is 6. Since I'm under the y, I'm going to go up and down 6 places. Now, technically, these are what I might call my co-vertices, which again are not technically on the branches, but will help us to actually do the graph. Okay, you'll notice here that I didn't even ask for the co-vertex points because we don't generally identify them since they're not actually part of the graph itself. Okay, now we do need to identify the focal points, which means we need the c value. Remember that a squared plus b squared equals c squared. My a squared is 25, my b squared is 36, and when I add 25 and 36, I get 61. And therefore, my c value is the square root of 61. The square root of 61 is approximately 7.8. And again, you kind of want to know both values. When I plot my focal points, I'm going to be using that 7.8 to estimate where they go. But when I write my ordered pairs, I am going to use my square root of 61 to be exact. Since the focal points, the vertices, and the center should all be on the same transverse axis. Sorry, I can't write that very well. I know that I'm going to have to put my focal points, I'm going to have to go left and right 7.8 because I have to still be going horizontally just like the rest of them. Now, when I go to write my ordered pairs, that means I went positive square root 61, comma 0, and I went negative square root 61, comma 0. And again, I'm using those exact points. Now, for the actual graph, we're going to come back and we're going to draw in lightly a rectangle connecting our co-vertices and our vertices. So I always just kind of slightly sketch in this rectangle, connecting all of those. Then I want to draw the diagonals of this rectangle. Make sure the diagonals go through the corners, otherwise you haven't drawn a diagonal. And again, we're going to draw this diagonal down here. And by drawing in those diagonals, remember these diagonals are going to act as our asymptotes. So now that I have the asymptotes drawn in, I can go back to these vertices and I can actually sketch in a hyperbola branch that approaches both asymptotes. So those asymptotes are going to act kind of as your guide so that you know how wide to draw the branches. So now I've got a pretty good graph of it. The last thing I need is the equations of the asymptotes. And again, yes, you can memorize those formulas, but you could also look back at your graph. So to write the equation of this line, y equals mx plus b, remember that it's going through the center, so that's plus 0. As for the slope of this line, I went up 6 places and I went to the right 5 places, so my slope is 6 over 5x. The slope of this line will be negative 6 over 5x, so the equations of my asymptotes are positive and negative 6/5 x. And again, you'll notice that the 6 was the b value, the 5 was the a value, so you could memorize it as b over a, or you could go back to the graph. Another example, notice the difference in this one. The format is not the same, but there are a few things that you want to see right away. For example, the fact that we are subtracting tells us that we are dealing with a hyperbola. Remember that an ellipse, you're going to see like an x squared plus a y squared. If you see a subtraction, and it doesn't matter what order, but if you see a subtraction, that's how you know that you're dealing with some sort of hyperbola here, okay? But the other problem, or the main problem here, is that it doesn't say equals 1. So we're going to have to start with dividing by 32. We're going to divide everything by 32. And that, when we reduce, that's going to give us this equals 1. So 2 divided by 32, that's going to reduce to y squared over 16 minus 8 over 32. That reduces to x squared over 4. Here's our equation of our hyperbola. Once again, my center is at 0, 0. So I'll plot my center right away. Because the y squared comes first, we know that this hyperbola is going to open up or down. And so then we're going to go our distances. The 16, that's my a squared, which means my a value is 4. Since the 16 is below the y, I'm going to go up and down 4 places, and those are my vertices. So my vertices are at 0, positive 4, and 0, negative 4. Now, in terms of my focal point, let's actually do our b value next. This 4, this is my b squared, which means my b value is 2. I'm going to go left and right 2 points. Those are my co-vertices, which I'm not going to name over here since they're not technically part of the graph. I can do this in any order. I can actually draw in right now. I could draw in my rectangle, connecting my vertices and co-vertices, draw in my asymptotes, or my diagonals of my rectangle. And then I can draw in the branches from those vertices. Oops, I forgot to switch, I apologize. Okay, we can draw in those branches opening up and down and using those asymptotes as a guide. So now I have a pretty decent graph. I still need my focal points. So we're going to go back to that equation. A squared plus b squared equals c squared. A squared is 16, b squared is 4, which means c squared is 20, which means c is square root of 20, which simplifies to 2 square root 5, and that is approximately 4.5 when we graph it. Now remember, these all have to be on the same transverse axis. So when I plot these focal points, I'm going to have to go up 4.5 and down 4.5. And we're going to have to put those focus points right inside those hyperbola branches. When I'm naming the focal points, use your simplified but exact value. So I was at 0, positive 2 root 5, and I was at 0, negative 2 root 5. So you can do one ordered pair or 2 separate, up to you. And for the equations of my asymptotes, remember the main thing is we need the slope of these lines. We already know that the graph goes through the center, which is at 0. In terms of the slope, we went up 4 units and right 2 units. So our slope is 4 over 2. That reduces to 2x. And the second asymptote will simply have a slope of negative 2x. So my equations of my asymptotes are positive and negative 2x plus 0, or you could just say positive and negative 2x. Okay. So if I gave you an example of one here where you had to write the equation yourself, this time it says that we have a hyperbola and we have one vertex at 0, 4. So I'm going to plot that point as my vertex. Now, not knowing where the center is, I can't plot the other vertex yet. Okay. But then it tells us that we have focal points at 0, negative 7, and 0, 7. So my focal points are here and here. Now, since I have both focal points and I know the center is right between them, now I know that my center is at 0, 0. Once I've established my center, now I can go back and place my second vertex at 0, negative 4. So I've got all of these key points placed. Based on these, I know that this is going to be a parabola that is going to be opening up or down, okay, up and down, I should say, so that because our transverse axis is vertical, and because it's a hyperbola, opening up and down, we know that it has to start with y squared minus x squared equals 1. We're going to have to fill in the a squared and the b squared. So now we can go back to the graph to get our a and b values. Remember that the distance from the center to the vertex, that's my a value, and in this case, that's 4, which means my a squared value is 16. And so I can put that 16 below the y squared since I did go up and down 4. As for b squared, I'm going to need to actually solve for that. So if I go back to the graph, I can see that the distance to the focus, that's my c value, that's 7. And then I can use my formula, a squared plus b squared equals c squared. If a squared is 16, c squared is 49, then b squared is 33. Now, technically, that means that b is the square root of 33, but it's really the b squared that I need for my equation. So if I go back over here, b squared is 33. And there's my equation. Now, I did have a second example here, but I think we've kind of seen a couple of them. I do have an answer to this one. It might be a nice idea to kind of go through and try this one on your own and see if you can come up with where these answers came from. And then I kind of ended with a few different hints. Remember that every hyperbola does have 2 branches. You'll have to decide if they open up or down, or if they open left or right. And that's based on, again, what comes first. If it's y squared minus x squared, then they open up or down. If it's x squared minus y squared, then these open left or right. The focal points and the vertices will always be connected by a line. That line that connects them is actually what we call the transverse axis. The midpoint of the transverse axis is that center. So remember, the center is going to be right in between the vertices, right in between the focal points. And remember, the other big thing I always like to remind people of is that the relationship between a squared, b squared, and c squared is actually addition with the hyperbola. So again, we're looking kind of at the opposites. If we see subtraction in the equation, we're going to see addition right here. And then the last thing I left with was the asymptotes. Remember that the asymptotes are going to be passing through the corners of the rectangle. That rectangle is formed by the vertices and co-vertices. We can quickly calculate the asymptotes by finding the slopes of those lines. And remember, since they're connecting the vertices and co-vertices, we're really using our a and b values to find those slopes. But you do need to pay attention to whether it's a over b or b over a, which is why I always say really look at the graph before you're writing your asymptote equations. Good luck, and later on this week we'll be looking at the same hyperbolas, but just shifting that center point around a little bit and seeing how that changes some of the focal points